Yeah, so we saw this video and then we thoroughly talked about this video, right? So what was the idea of this video? So now let us move on ahead and then so bit by bit let us understand what did we learn from the previous class, right? So that was clear that we clearly studied that the universe started with a Big Bang, right? What is a Big Bang theory? So yeah, let me put it in the presentation mode and then we can start. Yeah. So what is a Big Bang theory? So discoveries in astronomy and physics suggest that the universe had a definite beginning, right? So it started with a Big Bang. And we'll talk about what are the important things about the Big Bang and what are the assumed things which are not correct. So universe started with the Big Bang, right? And this is the prevailing theory, right? Which correctly predicts all the observations that we have for our universe. So this is the most accurate theory of the beginning of the universe, right? From the beginning and from the first element, first atom which was produced or which was developed, right? Which was formed. So the beginning of the universe is told correctly predicted by this Big Bang theory, right? And then, yeah, it is considered to be the best theory of cosmology, right? Because as we have discussed that it correctly predicts and it accurately explains all the observations that we have in the field of cosmology, right? So this is the Big Bang. So the most accurate theory of the beginning of the universe is the Big Bang, right? And what is the Big Bang? So in the beginning of the universe, 13.7 billion years ago, it started with a Big Bang, singularity, right? So the universe was a singular point, right? What is a singularity? Can anybody explain me? What is a singularity? Yeah. So singularity is a term in which all the physical phenomena that we have, all the physics theory that we have, that is discarded, right? So every theory of the physics that we have, we cannot explain that point, that singularity. So every theory of physics fails at this point. That is singularity. Because how can you explain a place with zero volume, right? So it has a zero volume but infinite mass because all of the things that are there in the universe that is constrained inside that zero volume, right? Volume is zero, which is very small. And in that volume, let's say that you are putting an elephant inside a bottle, right? So that is a very absurd thing. That is what we call a singularity. We can't express those things in physical definitions, right? So every definition of physics that fails in that singularity. So from that singularity, the universe started to grow, right? The universe expanded. And that created space and time, right? So the space, time, energy, everything formed with that Big Bang. And yeah, matter, energy, space, and time all begin inside that singularity. So from that singularity, from that Big Bang singularity, everything started to form, right? And then as the Big Bang happened, so the universe started to grow, it started to expand. And if something expands, the temperature of the universe cools down. And the universe, because now in the zero volume and infinite density, you have a very dense thing, right? But as the universe starts to grow, as the universe starts to expand, the density becomes lesser and lesser, right? So the density becomes lesser and lesser, and the temperature cools down. And then we have different phases. right? So that is what we call the Big Bang, right? So the universe is still expanding today, and in 1998, it was observed from the supernova experiment that the universe is not only expanding, but it is accelerating, right? So there were some groups of physicists and whose names were Saul Perlmutter and Adam G. Rees. So they got the Nobel Prize for that discovery that the universe is accelerating. So currently, in current time, the universe is accelerating, right? So not only expanding, but it is accelerating, right? And it was observed by the two groups, Sol Palmeter and then Adam Jeeves. And they got the Nobel Prize, right? So that is about the Big Bang Theory. It started from a singularity, then matter, energy, space, and time were created. And then the universe started to expand, right? And as the universe started to expand, then the temperature of the universe cools down. And then we have different phenomena subsequently happen. And all those phenomena contribute to whatever we have in our universe. So all those galaxies, all those stars, whatever we are, so all those things are due to the physics that happened 13.7 billion years ago. So the age of the universe is 13.7 billion years. That is the age of our universe. Right. So this is the thing that we talked about in that video. And then, so what was the Big Bang which was new? So what are the assumptions that is not right about the Big Bang, right? So as it appears that it is bang, right? Big Bang meaning a big explosion. But it was not actually explosion. It was the sudden expansion of the universe, right? So it was not an explosion. So this is the wrong assumption. And then the universe didn't appear somewhere in space, right? So let's say we are in here and then universe started from here. Not, it is not correct. So the Big Bang created space and time. It didn't appear from somewhere at random, right? So the Big Bang itself created the space, time, and energy. That is, so these are the two wrong assumptions about the Big Bang, right? And then, yeah, so the Big Bang created space and time. This is the correct explanation, right? So did you guys understood about the Big Bang? Now, do you understand about what was the Big Bang? Yes, guys, clear. Yeah. So that is the Big Bang that we have. Now, what is an expanding universe, right? So these in this video, in this description, we'll see that what is the expanding of the universe. So they are not moving far away, which means that these ants are not moving far away from each other, right? What is happening is that the place that these ants are residing, that place is expanding, right? Not these ants. So this is the correct explanation of the expanding of the universe. So space is expanding, right? It is not like that these ants or these galaxies are moving away. The space itself is expanding, right? So can you tell me about one thing, right? Let's say that, yeah, there is a very beautiful example that explains this theory. Let's say all of you guys know about the coordinate system, right? All of you guys know about the coordinate system, right? So let's say we have this X. What is Why can't I write in this? Yeah, so let's say we have this. So let's say we have this x and y axis, right? Now, what happens? It's very troublesome. So let's say that what do we do in the coordinate system? What do we do? So we point out the coordinates in equal space. Let's say this is 1, 2, 3, 4, 5, and let's say this is minus and something like that, right? This is 1, this is 2, this is 3, this is 4, and this is 5. So every location, right? Let's say that this is this location. What is this location? Can anybody tell me what is this location? What is this location?
Origin.
This one. This one is origin, right? Yes, this one is origin. This one is 2 comma 2, right? And then let's say I talk about let's say this point, this one. So this point is 4 comma 4, right? So now this point and this point, what would be the distance between these 2 points? What, let's say this is A, this is B, right? And now, can you tell me that what would be AB? Yes, anyone can tell me. This is simple 10th mathematics, right? All of you guys are in 10th or maybe 11th, 12th, right? So can anybody tell me what is this distance AB? What is this AB distance? Anybody? This is simple distance formula, right? Root of y2 minus y1 or x2 minus x1 whole square. So let's say 4 minus 2 whole square. And then this is 4 minus 2 whole square, right? So this would be 2 square plus 2 square. So this is 4 plus 4, so root 8, which means 2 root 2, right? Now I associate some coordinate points, right? I associate some coordinate points to each of these, let's say some x1, y1, x2, y2, x3, y3, and so on, right? So these are some distance between these ends, right? Now, if the universe, the space itself, so let's say I zoom in this thing, right? I expand this thing. So now what will happen is that now this would be 1, right? This would be 2, this would be 3, this would be 1, this would be 2, this would be 3, and this would be 4. So whatever this point was, this was 2 comma 2, and this was 4 comma 4, because the universe itself has expanded. So these 2 points were near, but you expand this space-time, you expand this space. So now these are the coordinates that you have. So now, can you tell me that will this AB change? Will this AB change? Yeah. Will this AB change? distance between A, B change? Yes, any one of you, will the distance be changed in this thing when you expand this thing and you are inside that thing, right? So will this distance change? Now the coordinates are same. So again, the distance would be root 8, which is 2 root. But physically, you guys can see that the physical distance, right, it is increased. So that is the idea of the expanding universe. Is this point clear to you guys? Although the distance between these 2 points remains the same because the coordinates are not changing, but the space itself is expanding. So that is why these distance are increased. The physical distance is increased, but the co-moving, so it is called the co-moving distance, that remains the same, right? Because the coordinates of these points remains the same. You can take the example of a balloon, right? And let's say there are no air in that balloon, and let's say this is some balloon, right? So this is some balloon, and there are no air, and then you mark 2 points, right? Now what you do is that now you blow up this balloon. So now this balloon is blown up, right? Now the distance between these 2 points will also increase. So now what you have done is that you have increased the space itself. That is why these 2 points that you have marked, these distance will increase. So that is the expansion of the universe. Is this point clear, everyone? Why you guys are so silent? So you guys have eaten your dinner, right? So yeah, so that is what we call the expanding universe. The space itself is expanding, but the distance between these 2 points, the coordinates remains the same, right? So they are not moving apart because of some past explosion, right? But the space itself, because of the universe expansion, they are moving apart, right? So this is the stretching of the universe, right? Now you can see that the distance between these ants, these are increased due to the expansion of the universe. And that is happening since the beginning of the universe. From this Big Bang singularity, the space is continuously expanding, right? So that is how you can predict that in the end of the universe, the temperature of the universe would be very cool down, right? So that is the expansion of the universe, right? And then, yeah, so how, let's say, this is the Big Bang singularity from where the Big Bang started, and then the universe expand. So now these galaxies, they move far apart from each other, right? And then they can form the planets, all those things, and all those structures that we see around us. So that is the expansion of the universe, right? Is this part clear, everyone?
Yes, sir.
Okay, good. So now let us move on to the other things, that what are the result for this expansion of the universe, right? So what are the byproduct of this expansion of the universe? What is it giving, right? So yeah, we understood about the beginning of the universe, that it started with some Big Bang, right? And there were no space before the Big Bang, right? So the Big Bang itself created the space, time, and all the other things, matter, energy, all those things. And then, yeah, so all these things are speculative. Why we call it speculative? Can anybody tell me the answer? Yeah. Yes. Why we call it speculative? Although these are very correct theories, but these are speculative, right? These are speculative because we cannot observe these things. right? We cannot observe inflation. We cannot observe the era before lepton and heteron era and all those things. We cannot observe. We can only observe the light which are coming from the recombination era. I will talk about what is the recombination era. So that is the end of this radiation era, right? So the beginning of the matter era. In the beginning of the matter era, you have this recombination where the electrons and protons are combining, and then they are making some lightest element, and then the light which is trapped, then it gets released, and only those lights we can observe. So those lights are called relic lights. And anybody know what is the name of those lights? There is a particular term for those lights. Can anybody tell me? What are those lights? What are those radiation called? You must have heard about that thing in so many, yeah, at some point of time. What are those lights? What are those radiation which were trapped? And then at the time of recombination, it got released. And those lights which are coming to us from the beginning of the universe. So after 360,000 years, those trapped lights, they got released. And those lights we can observe, not before that. So that is why all those things which are happening before that period, those are called speculative. But they correctly predicts all the observations that we have subsequent. So that is why we call it a perfect theory. But those ideas are speculative because we cannot observe all those, right? Okay, so yeah, the first at the beginning of the universe, this small time, 10 to the power minus 43 second, is called the Planck era, in which all of those forces, the gravitational force, electromagnetic force, weak interactive force, strong force. So in physics, you have only four forces, right? And all those in whatever we see around us in the nature, all those are combined with all those four forces that we have. So we can explain everything about the nature with the use of all those four forces, right? So at the beginning of the universe, all the four forces were combined, and the size of the universe was very small, at the size of the Planck length, right? And we don't have any particular theory to explain those phenomena. That is why we call it the singularity, Big Bang singularity, and then we have the Planck era, right? In the Planck era, the size is very small, and the gravity that can explain that era is called the quantum gravity, right? So quantum nature of the universe was more dominant because the size was very small, and we cannot accurately predict the position and all those things, right? So that is why the quantum nature is prevalent in those areas. So that is what we call the Planck era, right? In the first 10 to the power minus 43 second of the beginning of the universe. And then after that, the universe is expanding. And then we have all those different eras that we have already talked about in that video. So let us again discuss all those things in detail. And the first thing is the fundamental. Yeah. So let us first understand what are the fundamental interactions. So the universe is made up of four fundamental interactions, right? And those are gravity, strong, weak, and electromagnetic interactions, right? And as we all know that all these were combined, right, in the Planck era. And yeah, so all these things were unified, right? And then the universe starts to expand, temperature cools down, and then the first thing that happens, so the temperature cools down to 10 to the power 32 Kelvin, right? Temperature cools down to 10 to the power 32 Kelvin. And after 10 to the power minus 43 second, gravity is separated from the unified interaction, right? So earlier, all those forces weak, strong, gravitational, and electromagnetic forces. All forces will combine. But when the temperature cools down to 10 to the power 32 Kelvin, then the gravity is dispersed from this unified interaction, right? And the timeline is 10 to the power minus 43 seconds, right? And then after that, the universe further cools down, right? And it cools down to this 10 to the power 27 Kelvin temperature. And this strong force, this is also separated, right? So all these things are happening in a very instant time, right? At a very instant amount of time. So 10 to the power minus 43 and minus 35. So how much is that? This is 8, 10 to the power minus 8 seconds, right? So that is a very quick time. In this time, this strong force is separated from this unified interaction. And then the universe further cools down, right? And then it reaches to 10 to the power 15 Kelvin, right? From 10 to the power 27 Kelvin to 10 to the power 15 Kelvin. And now all the forces are separated. So now, if all the forces are separated, then we can have different elements, right? So this is 4 into 10 to the power 17. Yeah, so this is what we have. This is today's time. In today's time, the time is 4.4 into 10 to the power 17 second, which is 13.7 billion years. And then the temperature now, right? The temperature now, the temperature of the universe now is 2.9 Kelvin. This is the temperature of the universe at current, right? And this is the relic temperature that was there for the CMB time. So that time is what we call the cosmic microwave background radiation, right? CMB radiation. So whatever we observe, that is the relic of that CMB time. So this is the speculative Big Bang theory, and it correctly predicts all those phenomena that we observe in our universe, right? So these are the evolution of matter, right? So in this time, 10 to the power minus 12 to minus 6 second after the Big Bang, we have quark era, right? So what are these quarks that we have already talked about, right? Can anybody tell me, or anybody remembers what we talked about these quarks? What are these quarks? Yes. What are these quarks that we have already talked about when I was discussing that video? So what are these quarks? You guys have forgotten. So we talked about that generally we think that electrons, protons, and neutrons, they are the fundamental things, right? But neutrons and protons, they can be further divided into sub fundamental particles, right? And those fundamental particles, although they are not stable, right? So stability is gained from neutron, proton, and electron. Although, yeah, in comparative to these quarks, they are stable fundamental units, right? But yeah, those neutron and protons, they are further divided into these fundamental units, which are called quarks, right? So those neutrons and protons are made up of these quarks. And they are formed after 10 to the power minus 12 and 10 to the power minus 6 seconds after the Big Bang. So in this timeline, those quarks, those are formed. Anybody, can anybody name some quarks that we already discussed? Can anybody name some quarks that we discussed in that video? So there were six quarks, right? Up, down, strange, charm, and yeah, all the other quarks. So top, bottom, up, down, and strange and charm. So these are the six quarks that you have. And neutron and proton, they are made up of three quarks. So those are the fundamental unit of those neutrons and protons. And after that quark era, you have these hadrons. So these quarks are combined together. Temperature has cooled down. These quarks combine together and they form hadron. And after 1 second, between 1 to 10 seconds, these leptons are formed. Right. So again, anybody know some examples of leptons? All these are fundamental particles, right? So particles are divided into hadrons or leptons, right? So can anybody tell me some examples of leptons? We talked about that thing in the previous class, right? If you don't remember, that is quite all right. That is totally all right. But can you name some leptons? You guys already know. You guys have already seen those leptons, and you guys must have done some calculation using those leptons, right? So anyone? No one. So some of the examples of leptons are electron. Electron is an example of lepton, right? And then neutrinos, so they are also the example of leptons, right? So they are formed after between 1 to 10 seconds after the Big Bang. And then we have these radiations, right? So after 10 to 300,000 years after the Big Bang, the universe is filled with light. Only light is dominant. That is why it is called the radiation era. In this era, the light was more dominant, right? The matter were not dominant. These lights were dominant. So that is why we call it the radiation era, right? And yeah. So what did you discuss? That the first few seconds were the quark era, right? Strong interaction is separated, and then the quarks are formed, right? And after yeah, because the quarks can feel these strong interactions, right? The leptons are susceptible to the weak interaction, but quarks can feel the strong interaction. That is why the quarks are formed, because the strong interactions are separated, and then you have these quarks. So these quarks are formed, and yeah. So okay, one point I missed, that the temperature of the universe was too high for these quarks to combine, right? So these quarks cannot combine together to form neutrons and protons. They require the cooling down of the temperature, right? Because the temperature of the universe was 10 to the power 27 Kelvin, right? At this temperature, the quarks cannot combine. So after the lepton era, we have these hadrons, because now the temperature has cooled down, so that these quarks can combine and they can form these protons and these neutrons, right? So you can see that these UUD. So this is up, up, down. So proton is made up of three quarks, which are up, up, down quark. And then this neutron is made up of three quarks, which are up, down, down. Right. So these are the substructure of these protons and neutrons. Because what has happened, the universe has cooled down, and with these strong interactions, those quarks can combine and they can form these protons and neutrons, right? Okay, so yeah. And then yeah, so after that hadron era, we have these leptons, because now in this era, the hadrons have been annihilated because of the antiparticles and particles. Now the only thing which is more dominant is this electrons. So you have these electrons and then positrons, neutrinos and antineutrinos and all those things. So between 1 second to 10 seconds, these leptons are more dominant, right? And then again, these leptons, because they are in equal numbers, these electrons and positrons, they are in equal numbers. So they annihilate each other and some amount of leptons are left, right? Yeah, so they annihilate and they give radiation. They annihilate and then they release photons. But some of the leptons, they are not annihilated, and whatever we see around the universe today, those are the remnants of those leptons which were not annihilated, right? Yeah. And after that, because antiparticle are interacting and they are making photons, so now universe is filled with these photons, these radiation. So that is why we call it the radiation dominated era. And this starts from the 10 seconds. So after the 10 seconds from the Big Bang, the universe is filled with those radiation lights, and the color of that universe is orange, right? So universe was full of lights, and then the temperature of the universe is cooling down, right? So these protons and neutrons, they are combining to form hydrogen and helium, and then they are releasing those radiations, right? So all these are happening, right? Because these neutrons and protons, they combine and they make this hydrogen and release this photons, right? And again, this neutron is combined with this hydrogen, right? So what is this isotope called? What is this called? Can anybody tell me what is this isotope called? To which? What is this thing called? All of you guys are in your 11th and 10th standard, right? So isotopes you have learned, right, in chemistry. All of you guys have studied about these isotopes, right? Yes. Atomic structure of atom you guys have studied, right? Yes or no? How many people are here? Yeah, so lots of people are here. So why can't you guys tell me? Right. So anybody who is not in 10th or 11th or 12th standard, who is in, let's say, 8th or 9th standard, you are in 9th standard, right? So, yeah,
Eight,
that question, 8th.
eight standard.
Okay. Yeah, okay. So, yeah, Ibrahim, these things would not be, yeah, more clear to you because these are complicated things, but just try to understand, right? At least if you understand 10 or 20%, so that would be enough. Right, because when you will go to your higher standard, higher studies, then you will learn about all these things, right? In chemistry and all those physics classes, so we learn about all these things, right? But yeah, so leaving Ibrahim, rest of you guys, all of you guys are in your 10th, 11th, 12th standard, right? So you guys have studied those structure of atom and isotopes, Bohr's model and all those models of atom. So this is deuterium, right? You have hydrogen has three isotopes, protium, deuterium, and then what is the third one? Yes, what is the third isotope? So third is tritium, right? So yeah, this deuterium is combined with this nitrogen, and it forms a tritium, and then it releases some photons. And then this hydrogen, when combines with proton, this forms this helium atom. And then again, because these are all nuclear fusion, right? Fusion. So nuclear synthesis is happening, and then nuclear fusion is happening, and all those things are being made, right? Okay. Yeah, so but these are not the atoms, right? These are the uh, nucleus. So these are all nucleus, not the atoms, and because no electrons are there, right? Because no electrons are there, so these are all nucleus. So these nucleus are forming. That is why it is called nucleosynthesis, because nucleus is forming. Synthesis is forming. Nucleo is related with nucleus. So nucleus are formed, right? And then, yeah, the all the lighter nucleus are combining together and they are forming the heavier nucleus. So this is what we call Big Bang nucleosynthesis, right? And then, yeah, okay, but yeah, so after this phase, this phase is happening around up to 300,000 years after the Big Bang. Hydrogen and helium nuclei have formed. Now they start to capture because the temperature of the universe has cooled down, right? And we require 13.6 kilo electron volt energy to capture to make one hydrogen atom, right? So that much a temperature we require, and when that temperature is reached, then this hydrogen and helium nuclei capture those electrons and they form these stable atoms. So the lightest atoms that are formed in the beginning of the universe are hydrogen and helium, right? All those things that you see around us, all those carbons, nitrogen, iron, and silver, and radiums, all those heavier elements that you see, those were not formed around that age, right? So only the universe was filled with the lightest elements that you have, hydrogen and helium, right? So 75% hydrogen and 25% helium. And yeah, the density of the universe is decreasing and the universe is cooling down, right? So after 370,000 years of the Big Bang, because all of the photons have been released, and now do we have where are these photons forming? Because now you don't have any photons, right? After 370,000 years of the Big Bang, you don't have any photons, right? You don't have any radiation. Can you guys tell me, so what would be the color of the universe at that age? Because all of the radiation have been exhausted. All of those photons have been exhausted. And whatever light that we see in the morning, that is coming from where? Where does this light comes from? Yeah. So in the morning, you see those lights. So where does that light come from? The light that you see in the universe now, that is due to what? Okay, very simple question. So whatever light that you see in the morning, that is due to what? When do we call the morning? Yes, this is a fifth, sixth question. When do we call, what is the time that we call morning? Whenever sun rises, that is what we call the morning, right? Right, everyone? Due to rising of the sun, you have morning and then day and nights. So day and nights are due to the rising and setting of the sun, right? So whatever light that we see on earth, that comes from the sun. Sun is a star. So whatever light that we see in the universe today, that is only due to the stars that is around us in the universe, right? Whatever light we see in the universe, that is due to the stars. Correct, everyone?
Yes, sir.
So, were there any stars after 370,000 years after the Big Bang? Were there any stars in that period? There were no stars, right? And because you don't have photons, you don't have stars, which means that you cannot see any light, right? There were no light at those ages. So that is why we call that age as dark age of the universe. Dark age of the universe because the universe is exhausted with this radiation photons, and there were no stars to release those photons. So that is why the age that age that is called, that is the dark ages. And after the dark ages, when those galaxies or those gaseous cloud of those hydrogen and those helium, they combine and they form these galaxies and these stars, right? So whatever stars that are formed, first stars are formed 100 million years after the Big Bang, right? So after 100 million years of the Big Bang, the first galaxies and stars are formed. So because of the gravity, those clouds of hydrogen and helium, they combine together and they form these galaxies and these stars, right? So after 100 to 200 million years, these stars are right. And then due to the fusion of these stars, the fusion is happening inside those stars, and then again we can see those lights. So there was some dark age of the universe in which there were no lights, and when the stars were formed, first stars after the 100 million years, they were formed, then the universe again started to glow. So that is the history of the first stars and the universe. And then the galaxies, when these stars are grouped together, they form these galaxies. A billion years, right? So before, how many years? 12.7 years ago, the first galaxies were formed, right? So and then these galaxies form together and they combine together and they form galaxy clusters. So stars combine together to form galaxies, and those galaxies combine together to form clusters, and those clusters combine to form a supercluster. And what is the supercluster that we live in? That I have talked about. Right, in the beginning of all of these lecture, I talked about that what is the supercluster that we live in? Anybody remember? Nobody remembers? Okay, so yeah. The supercluster that we live in, so that is this supercluster. This is the supercluster that we live in, right? This is what we call Laniakea. Right. Inside that universe, this is the supercluster. And inside that supercluster, we have our own galaxy, Milky Way. Inside that Milky Way, we have solar system. Inside that solar system, we have these planets. So all these planets were formed after the formation of those galaxies, 2 billion years, 1 billion years after the Big Bang, right? So that is so fascinating, right? And yeah, so this is the history of the universe. Whatever we are, all started 13.7 billion years ago. And this completes the theory for this lecture. And in the next class, right, so after 8.4 billion years, right, after the Big Bang, you have these solar system. So whatever the solar system that was made after 8.4 billion years. So what, 2 billion years, galaxies are formed, 1 billion and 2 billion years, galaxies are formed. And after a very long time, billion years, 8.4 billion years after the Big Bang, these planets, solar system and all those things are formed, right? So yeah, there is a very beautiful video that depicts the timeline of the universe, right? So I will send this video to all of you and you guys can see this video, which depicts very beautifully the timeline of the universe, right? So yeah, you guys can see this video and then you can understand that how the universe started, right? What is this song? Yeah, so this is a very beautiful video. Started with the Big Bang and then the age of the universe is 140 million years ago, right? And these stars and these galaxies are formed, right? Okay, so let me stop that and yeah, so this is completed, right? And then in the next class, I will talk about these simulations, right? So I will, yeah, please come with this Windows, right? And operating system, and then I will send you the uh, yeah, zip file of this program, right? So yeah, do I have? Yeah. So this is the zip file that we have. I will send you, or maybe I will send you this setup. So this way I will, okay, this is 1.27 GB. Maybe I will send you this, yeah, whatever is feasible to you guys. I will send this thing to you. And then we can install this thing and then we can understand about this simulation, which we are going to do. So we are planning to do 2 simulations. Right. Now you guys understood about our universe, the beginning of the universe, right? So yeah, and now in the next class, I will talk about this simulation. So we'll try to learn this simulation. We will run this program and we'll understand about all those gravity, all those planetary system, all those different galaxies, asteroids, and clusters, all those things. So that we will do in the next class. Right. We'll stop here. Why this is, yeah. So this is the thing that we'll do.